Hi there. Today we're going to look at end-to-end object detection with transformers by Nicolas Carrion, Francisco Massa, and others at Facebook AI Research. So on a high level, this paper does object detection in images using first a CNN and then a transformer to detect objects, and it does so via a bipartite matching training objective. And this leaves you basically with an architecture that is super simple compared to the previous architectures that had all kinds of engineering hurdles and thresholds and hyperparameters. So really excited for this. As always, if you like content like this, consider leaving a like, a comment, or subscribing. Let's get into it. So let's say you have a picture like this here, and you're supposed to detect all the objects in it, and also where they are and what they are. This task is called object detection. So a good classifier here would say there's a bird right here. And so this is a bird. And then this here is also a bird. Right? They can be overlapping, these bounding boxes. So this is, you see, the first problem that... bird. Why is that green? Never mind. Okay, and those are the only two objects. So there's a number of very difficult things here. First of all, you need to sort of detect the objects. You need to know how many there are. It's not always the same in each image. There can be multiple objects of the same class. There can be multiple objects of different classes. They can be anywhere of any size. They can be overlapping in the background, small, or across the entire image. They can occlude each other partially. So the problem is a very difficult problem. And previous work has done a lot of engineering on this, like building detectors, and then kind of you want to classify every single pixel here, and then you get like two detections right here that are very close for the same class, and you say, that must maybe be the same instance, right? So there's only one thing here and not two things, and so on. So there used to be very complicated architectures that solve these problems, and this paper here comes up with a super simple architecture, and we'll kind of go from the high level to the low, to the implementation of each of the parts. So what does this paper propose? How do we solve a task like this? First of all, we put the image, and the image here without the labels, of course, we put it through a convolutional neural network encoder. Since this is an image task, it's, kind of understandable that we do this, mostly because CNNs just work so well for images. So this gives us this set of image features. And I think this vector here is not really representative of what's happening. So let's actually take this picture right here and draw it in kind of an angled way. And what we'll do with CNN is we'll simply sort of scale it down, but have it multiple. So here it's 3 channels, right? It's red, green, and blue, like this, 3 channels. But we'll scale it down, but we make it more channels. So, so more channels. Okay, but it's still sort of an image right here. It still has the image form. Okay, so the CNN basically gives us this thing, which is sort of a higher level representation of the image, with many more feature channels, but still kind of information where in the image those features are. And this is going to be important in a second, because now this thing, which is this set of image features, goes into a transformer encoder decoder. And this is sort of the magic thing here as a component. We'll look into that in a second, but what they get out right here is this set of box predictions. So out comes, each of these boxes here is going to be consisting of a tuple, and the tuple is going to be the class and the bounding box. Okay, so an example for this could be bird at x equals 2, y equals 5. Okay, that's an example. Another example of this could also be there is nothing at x equals 7, y equals 9. Okay, so nothing, the nothing class is a valid class right here. And that's also important. But safe to say there's this set of box predictions, and then that is basically your output, right? These things are your output. If you have those things, you can draw these bounding boxes, you can assign the labels. The question is, how do you train it? Now, what you're given is a database of images, and these images, as you see here on the right, these images already have, by human annotators, drawn these bounding boxes in, and also labels. So this here would be annotated with bird, and this here would be annotated with bird. But it doesn't have any of these, like, it doesn't annotate the nothing classes and so on. So the question is, how do you compare the two? Can you simply say, okay, if the first one here is the bird, and the second one is this bird, then it's good. But then, you know, the ordering shouldn't matter. You simply care whether you have the correct bounding boxes. You don't care whether you output them in the correct order. And also, what if your classifier does something like this? It outputs those two boxes we see here, but it also outputs this here and says bird, or like one that is slightly off and says bird, and so on. So how do you deal with all of these cases? So the way that this paper deals with all of these cases is with their bipartite matching loss, this thing right here. So how does it work? Let's say where can we go? Let's say your classifier, so here is an image. I'll have to wait for this to catch up. Here is an image, and we put it through this entire pipeline, right? And we get a set of predictions, right? And they're going to be class bounding box, class bounding box, class bounding box. Now, the first thing you need to know is that there are always the same amount of predictions, right? There are always, this size here is fixed. That's large N, okay? That's kind of a maximum of predictions. Since you can always predict either a class or the nothing class, in this case, you could predict anywhere from 0 to 5 objects in the scene, right? Okay, and then the second thing is from your database, you get out an image with its bounding box annotations, right, that are made by human labelers. Let's say these two, and you also do class bounding box, class bounding box. But now you see we only have two instances. So here we just pad with the nothing class. So I don't know what the bounding box should be for the nothing class. It doesn't really matter. Nothing, no bounding box. Nothing, no bounding box. No bounding box. So your ground truth labels, if you will, are also of size n. So you always compare n things here on the left that your classifier output with n things on the right. Now, as we already said, the question is, how do you deal with, you can't simply compare one by one because the ordering should not be important. But also, you don't want to encourage your classifier to always kind of, if the one bird is very prominent, right? You don't want to encourage your classifier to say like, here's a bird, there's a bird right here, hey, there's a bird, there's a bird, and basically just because the signal for that bird is stronger, and basically ignore the other bird. What you want to do is you want to encourage some sort of your classifier to detect, if it has already detected an object, it shouldn't detect it again in a slightly different place. So the way you do this is with this bipartite matching loss. So at the time when you compute the loss, you go here and you compute what's called a maximum matching. Now, what you have to provide is a loss function. So there's a loss function, L, and L will take two of these things. L will take the predicted thing of your model, and L will take one of the true underlying things, and L will compute a number, and will say how well do these two agree. So you can say, for example, if either of them is the nothing class, then I have no loss. Like, I don't care about them. That gives you no loss. But if the two classes agree and the two bounding boxes agree, then it's very good, right? Then we maybe even give like some negative loss or give loss 0. But if the bounding boxes agree, but the classes don't agree, then you say that's bad. Or the other way around, if the classes agree in the bounding, or even if everything disagrees, it's the worst, right? What you're basically saying is if these two would correspond to each other, right? If the thing on the left were the prediction for the thing on the right, which we don't know, right? It could be that the thing on the right refers to the bird on the right, and the thing on the left refers to the bird on the left. So it would be natural that the bounding boxes are the same. But you say if these were corresponding to each other, what would the loss be? How well would they do? And now if you compute this bipartite matching, what you want, I guess it's a minimum matching in this case, what you want is you want to find an assignment of things on the left to things on the right, a one-to-one assignment. This is an example of a one-to-one assignment. Everything on the left is assigned exactly one thing on the right, such that the total loss is minimized, right? So you're going to say, I'm going to align the things on the left with the things on the right, such that it's maximally favorable, right? I give you the maximum benefit of the doubt by aligning these things. And so in the best possible case, what's the loss? Okay? I hope this is somehow clear. So you're trying to find the assignment from the left to the right that basically is the best case for this output right here, where you really say, oh, okay, here you output a bird very close to the bird here in the ground truth label. That's this here. So I'm going to connect these two, because that's sort of it gives the model the most benefit of the doubt. And the loss that you have at the end of that matching, so this loss here would only then count wherever these connections are. That loss is going to be your training loss, okay? So this solves the problems we had before. It is not dependent on the order, because if you reorder the things, your minimum matching will simply swap with it. It is if you output the same bird multiple times, only one of these is going to be assigned. So if this here is that bird, only one of them, only this one maybe, is going to be assigned to that one. And the other ones can't be assigned to that one, are forced to be assigned to a different one, let's say this one here, and are going to incur a loss. So you encourage your model to output, let's say, diverse bounding boxes, different bounding boxes for things. Okay, so this solves these problems. And it's very clever. And there are algorithms to compute these minimum matchings. They use the Hungarian algorithm, which will give you exactly such a matching. Again, this is possible because you have n things on each side. And the n is, in effect, here is the maximum of objects that you can detect at once. I guess if there is less, you can simply pad right here. And then the model, of course, is encouraged to come up with the equal number of no class predictions, because if it outputs a prediction when it shouldn't, right? If it already predicts two things and these are assigned to these two things, and then it outputs one more thing, it is going to be penalized, because it should output three things with no class, but it has output one too many with a class, is going to be penalized. Okay, so this is a pretty cool thing. It relies on the fact that you have n on both sides, but you can make n so large that basically it covers all of the cases. So you can make n like 50. So you can detect up to 50 things in a scene. All right, that's the algorithm in a high level. They do show their loss here. You see, the loss ultimately is going to be over this matching right here. That's the minimum bipartite assignment that basically minimizes this total loss over your prediction and label matchings. And the loss they come up with here, I said you have to give the algorithm a loss, is this one. and they kind of go into how they do it. I don't think it's super important. So the class algorithm, sorry, the loss on the class labels, I think is going to be a softmax or a cross entropy loss, like in usual classification, and the loss on to say whether two bounding boxes agree is a mixture of the L1 loss that compares two bounding boxes and this IOU loss, which is not dependent on the scale of the bounding boxes. It kind of computes how much fraction of the two bounding boxes overlap. But in any case, the loss basically consists of saying how much do the labels agree and how much do the bounding boxes agree. Okay. Again, this is only possible because after that you compute this matching. Otherwise, you would have no clue which boxes which predictions to compare to which other predictions. So let's look at this architecture a bit more in detail. As we said, you have this, what they call the backbone, which is a convolutional neural network. And with that, you put in some positional encodings. Now, I already said you should look at these features right here as just smaller feature versions of the image, but they still have some image nature. Then they are flattened. So once they are put in the transformer encoder, because the transformer is naturally a sequence processing unit, okay? So it takes in just a sequence of vectors right here. And since an image is not a sequence, what you'll do is, if you have your image features, and we said we have a bunch of channels, let's say we have 4 channels, and they're of height and width and C, you're going to unroll and flatten that into one sequence. So this is height times width. You basically unroll across these axes right here into this axis, and it's channel size. So basically you have a sequence here of C dimensional feature vectors that you then put into your encoder. Okay, so your encoder will now transform this sequence into an equally long sequence, yet again, of features. And the good thing about a transformer, because why do you use a transformer? The good thing about the transformer is that in such a sequence, and I've done videos on transformers, you can mainly look at the video Attention is All You Need if you want to understand this more fully. This thing can basically have attention, so it has attention layers. It can attend from each position to each position in a one-shot manner. So as it transforms this representation up the transformer layers, at each step, it can basically aggregate information from everywhere in the sequence to anywhere else. And therefore, it's very powerful if you have a sequence and you need sort of global connections across the sequence. This is very good for language processing, because in a sentence, let's look at this sentence, the input images are batched together, right? Applying blah, 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 and then there's they, right? The word they. And you need to know that they refers to the input images, okay? But you see, this is very, very far away in the sentence. So you need a model that makes use of long-range dependencies. And they make the case that in such a task right here, you also need the long-range dependencies, because these bounding boxes, as you see right here, they can be quite large. So if you have an image, you need that this part here communicates with this and this and this and this part, basically anywhere in the bounding box. And these bounding boxes can be quite large. So the transformer architecture actually makes sense here. Now, I want to go a bit later into why I think it actually makes even more sense for bounding box detection, but right now I just want to keep going through this architecture right here. So if my computer here decides to come back, yes, we can go on. So what we'll get out is yet another so in here we put this thing we put down here. We put into the transformer encoder, and we get an equally sized, equally shaped sequence out of the transformer encoder. And you see that this thing here goes as a side input into this transformer decoder. So the transformer encoder here is just a bit more of a feature mapping. Technically, just for the architecture, you could think of just putting this into here. But of course, it's going to go better with the transformer encoder. The transformer decoder now does something similar, but you see it has the encoder as a side input. This is very much like, this is not like BERT. BERT is like a only encoder transformer, whereas this is much like the original attention is all you need transformer that has an encoder, and then the decoder as a side input, basically as conditioning information, has the encoder output. What does the decoder do? Again, since it's a transformer, it's going to take a sequence and output a sequence. The sequence it takes is right here, is what they call object queries. And this also is different from the attention is all you need papers, and they don't do it auto-regressively, they just do it one shot. What does it mean? It means that you start with a sequence here of 4 things, and this is this big N, and you output the sequence of a sequence of 4 things. And it's important to see what they're going to end up. So these things are then directly going through a classifier that now outputs the, so these things here are these class label bounding box outputs, okay? So each of these things is going to, after transformation, end up being one of these bounding boxes, either defining an object or saying that there isn't an object somewhere. Okay, you see here, this bounding box refers to this bird, this bounding box refers to this bird. So each of these things is going to be one bounding box. And what they call object queries is, the question of course is, what do you input here, right? I want to transform this image information that comes from the left here. I want to transform that into the bounding boxes. What do I input here? And the answer is, you just input at the start, you just input n random vectors, because what's that going to give you is basically n outputs. You want n outputs because you want n of these bounding box classifications. So you need n things, and if I input n things into a transformer, it's going to give me n things as an output. And then in each step I can simply condition on the information that comes in the images, and it'll give me, right, then I can incorporate that information. It's a very deep learning way of thinking about it, actually, is that you just need the information somewhere in there, and I need n things. Now they go more into detail into this transformer architecture, help in a helpful fashion in the appendix, and we'll go there quickly. So this, I think, here makes more sense. So the image features come in here, right? And you see this is just a transformer stack, an encoder stack of multi-head self-attention and feed-forward instance-wise or like token-wise feed-forward network. And then that information is taken and is given as conditioning information over here. Now in here, as I said, you input these object queries, which at the beginning are just n random vectors. And what you're going to do, you are also going to feature encode them, and then you combine it with this image information. So ultimately, if you think of this, of one of these things is going to be a vector, right? And then that vector is going to be transformed, and then it will have, as it is transformed, it will have the opportunity to basically look at features that come from here. Now the arrow is in the wrong direction. So you have already taken the image and you've transformed it into a feature representation, which is also a vector, right? You have the features of the image right here. Now, as you transform this vector, this object query, Q, you have the opportunity to look at the image features, right? And that's how you get the image information in there. So the image features will come in here, transform that through attention. So this is an attention mechanism on the image. And then what you will output is a bounding box and a class label. It's really hard to explain. I would guess you need to understand really what attention mechanisms are. And of course, the crucial part of course is what's this? What do you input at the beginning? And these object queries aren't actually random, as I said, they are learned. So what you're going to do is you're going to learn, independent of the input image, you're going to learn n different object queries. And these object queries now, it's very interesting, because these object queries are sort of going to be different. It's like you have different people that can ask the input image different questions, right? And this, they have, so their n is 100, but they show 20 of these object queries that they learn. And so they have visualization of all bounding box predictions on all images. So it's sort of like you have n different people at your disposal, and you train these n different people to kind of ask different questions of the input image, okay? You say this person up here will always ask, irrespective of what the input image is, will always ask sort of, hey, input image, what's on your bottom left, right? I'm really interested what's on your bottom left. And sometimes I'm a bit interested in what's here, but I'm mainly interested in what's on the bottom left of the image. Whereas this person right here, is more interested in what's in the center. Now the different colors here refer to different sizes of bounding boxes. So this person is also interested, so the person on the top left is interested mainly in, I think, small bounding boxes that are on the bottom left. And the person here is mostly interested in I'm really interested, what's in the center, what's large in the center. I want, give me large things that are in the center, right? And then this person right here is really interested on stuff that's on the right side of the image. So you see, in order to get different, sort of a difference in bounding box predictions, you train n different people to ask different questions of the input image. And this asking of questions is exactly what an attention mechanism is. So this person right here, let's take this person. And I'm saying person, these are vectors, these are learned object queries. But this person, first, they will simply ask the question, what's on the right side? And then the image features, right? I'm getting bored of drawing. The image features, it will have an attention mechanism to this part of the image features. And then it will get back some signal, right? And then it will transform that with its own signal up, and then it will ask maybe again, okay, now that I know more, because you see that person is interested in multiple things. It's interested in those things and those things. So at first it will focus on these things, but then it says, now I know more, right? I see there is actually something on the right side. So in the higher layers, it can then go back and ask the image more questions by sending these Q vectors of the attention mechanism. And it will get back the V vectors from the image features that correspond to these Q things. So up and up the layers, this person can ask more refined questions about what that particular person is interested in, okay? And since you have the different people here that ask different questions, you basically learn the people in a way such that across the data set, they cover every possible image pretty well. Again, these people, what they're interested in initially is not dependent on the picture. You simply learn this in a global manner. All right? This is the best way I have of describing it. You basically learn n people that are, each one is interested in different things, different classes and different regions in the image. And each one of these people is going to output their best guess of what is where based on what they're interested in. So that person might say, I'm the person that's interested kind of in the left side of things, so I'm going to output that there's a bird right here. Now these people, if this is a transformer, right, and everything can attend to everything, they can actually communicate with each other as they incorporate information from the image. So in each layer, they can do both. They can incorporate information from the image and they can communicate with each other. And then in the next layer, they can do it again and again and again. And thereby, they can sort of say, well, you already got the left side, I will take the right side. You already got the bird class, I will take the elephant class, and so on. So you see here how the architecture of the transformer actually is also very conducive to doing this bounding box prediction, in that these different things can sort of attend to each other and therefore communicate with each other. All right? I hope that sort of makes sense. Now, before we get into the experiments, I want to list a third reason of why the transformer, especially the encoders, might actually also make a giant amount of sense. Here, since you unroll the image into height and width, and you have to imagine, what does the transformer do? The transformer, as we said here, has this notion of attention, where from any point in the sequence, it can gather information from any other point in the sequence. And that's usually one of the downsides of the transformers, is done via a quadratic attention mechanism. So if I just list one feature channel, I'll go over here. If I just list one feature channel, right here, this is height times width of the image, right? This is the entire image unrolled in one vector, height times width. And here I unroll it again, height times width. Then this matrix that I can build right here, which is called the attention matrix, right here, it will tell me which parts of the sequence attend to which other parts, okay? So if you have an image that has let's say the number 3, and you really want to figure out whether or not this is a 3, then the bow up here must communicate with the bow down here, right? They need to share information to say, there's a bow here, and there is a spiky thing here. That must be a 3. So you want something, this is rather at the beginning of the sequence, you want this to attend, first of all, it will attend itself, so you'll get fairly high values along the diagonal, maybe 10, 10, 10, 11, 11, 12. I saw this Ollie G skit. 100 million, 9. But it also, like this part here, at the beginning of the sequence, let's say it's here, because this is unrolled, right, needs to attend to the end. So this needs to attend to the end, which we will put an 11 here, and the other way around. It doesn't always need to be symmetrical, by the way. Okay, but in any case, this is going to be a H times W squared matrix, because everything can attend to everything, and that's the attention mechanism. Why do I think this is so good for bounding boxes? Because let's imagine you actually have a matrix that is like this, okay? Height times width times height times width. Every single point in here actually defines a bounding box, because this point right here in this dimension corresponds to one location in the image, and on this axis it corresponds to another location. Now in the attention matrix simply means these 2 points need to communicate, but if you have 2 pixels, you actually have defined a bounding box right here, right? You're defining a bounding box, and the fact that this is happening in the exact same matrices could mean that the transformers are the transformers across sequences of these height times width unrolled images are uniquely well conducive to these bounding box prediction tasks. I'm actually a bit astounded, because when I first just read the title, this immediately popped to my mind. I'm like, oh yes, of course. And they're going to predict the bounding boxes by simply training. So what you would do, what I thought this was going to be, is you output an actual matrix like this, and then you simply each point you can simply classify, right? So you can classify here whether or not, like, in this direction there is a bird, right? And then if you have 2 points like this, for example, you also classify whether in this direction there is a bird, right? And this naturally defines a bounding box. Or you could like take this matrix and actually just classify individual points in this matrix to be the bounding boxes, because they already define bounding boxes. So I think these quadratic things are uniquely, I mean, someone must have thought of this, or if not, cite the YouTube channel. It would be funny. First paper ever to actually have to cite the YouTube channel. But again, yeah, so transformers seem to be a good idea for these kinds of things. So how do they do? Of course, they do well. They are on par with these other much more complex architectures, these faster RCNN models. They are apparently much more complex, but they are on par with this. They do, however, train forever. I think they train for like 6 days on 8 GPUs. It's not that much if you compare to like language models on hundreds of TPUs, but still. Okay, I don't want to go into the numbers of experiments, but what is pretty cool is that they can now visualize this sort of attention. And you can see right here that if they look at a particular point in the image and visualize the attention, it will actually attend to the instance itself. So it will, like, these are usually the problems for these detection algorithms when things overlap and are partially occluded. But you can see right here that the attention is on the part of the image that makes the instance in the back, and the attention here is on the part of this, and it doesn't sort of overlap into the others. So that is one thing that's pretty impressive about these architectures. The other thing they show is, for example, it can generalize to many instances. So here it has never seen 24 giraffes in one image, but yet it can absolutely do that. And giraffe. And the one of the coolest images I find are these here, where you can see right here, again, attention visualization, and you see that even within the bounding box of the front elephant here, you see that the attention on this foot of the back elephant is assigned to this blue bounding box. So this is the blue, basically the blue bounding box person that is attending to that back foot. That means these things really sort of understand, or they learn these things like occlusion and I have a hard time describing it, but you can see it visually here, right? Like how it clearly learns that these are two instances that are sort of occluding each other, but this instance can actually appear within the bounding box of the other instance. And the same goes for the zebra here, that are partially occluding each other, and you can see that the attention is correctly, like even here, this back foot of this zebra is correctly labeled. So all in all, that is pretty cool. And they take it a step further and they say, well, with this architecture, we can actually pretty easily do pixel-wise classification. So this is this COCO stuff and things data set where I don't know which one is the stuff and which one is the things. I think things is the objects and stuff is like sky and mountains and so on. And so this is a classification task where you actually have to label every single pixel. So what they do is they simply input this through their detector, and they detect the instances. They take the attention maps of the instances, and then they scale it up. This right here is just a CNN sort of in reverse that scales up the image because they have scaled it down. As we said, they scale it up again, and then they can simply classify each pixel where each of these, you remember we had these different people here that cared about different things in the image. Each of these people will classify their respective pixels, the pixels they feel responsible for, and then you simply merge all of these people's predictions together into this prediction. And again, this gives pretty impressive results. This is fun. This looks like it sort of works. They do quantitative analysis, of course, but I'm just impressed by the examples right here. All right, that was sort of it. I really enjoyed reading these papers. The simplicity is pretty cool. They do have, not only do they have code in the paper to show how ridiculously easy it is to get this to run. This is all you need in PyTorch, but they do actually have code. And as I understand, they also have pre-trained models. So they have this model zoo right here, where they give you the pre-trained models, so you can play with it, and you can even load it from TorchHub yourself, and you can train it yourself. They have a collab. All is there. All right. Again, if you enjoyed this video, consider leaving a like, subscribing, and I'll see you next time. Bye-bye.